This is the setting. At this point, we've now come to a right understanding of the premises of the problem. Right? Notice we put in a fair amount of work here, right, just to understand what the problem is saying. And we should always do this before we launch directly into an attack on the problem. I know that long tradition and custom through your early school years has brought in this instinct to just dive into a problem. But any worthwhile problem needs introspection, needs thought, needs time to understand what is going on. And this will well repay you. At this point, we've understood how to write down the a priori probabilities. We learned to write down the forward conditional probabilities. But the question at hand is, can I reverse the direction of conditioning? But for now, we're equipped to do this. Let's move directly onto this. Let's start with a simple question. Given that the second ball drawn is red, so you're looking at the second level of the tree, and you're looking at the red transitions to your left. Given that one of those happened, what are the chances that the first transition was to the left? Okay, let's build it up one step at a time. Our first question. What are the chances that the first two balls drawn are red? Well, from a formal mathematical point of view, the events at hand are R1 and R2, and we want the conjunction of them, the intersection of them. We write down an expression like this, and we can just read this out from the table. Well, what have we used here? We've used the chaining principle from the definition of conditional probability, which expresses the desired probability of R1 intersection R2 in terms of the a priori probabilities and the transition of the forward conditional probabilities. What can we say about the probability that the second ball is red? Formally, we want the probability of the event R2. And we can write down an expression, as you see, emerging on the right of your screen. Write it down, pause, absorb it. What is the guiding principle for an identity like this? Did you recognize the use of total probability? We broke up the sample space into two pieces, R1 and the complement of R1, or B1. This was a natural partition which is given to us by the structure of the problem. Given that partition, we now have a formal expression. But in this expression, we can read out all the relevant probabilities by looking at the vertices, the a priori probabilities, and the transitions. And there you go. It's as easy as that. We've now got a sum of two fractions, and now all that remains is to massage it using ordinary algebra, collect the denominators, pool the numerator terms, factor them, cancel out common factors, and we've got a beautiful, simple, elegant expression. The probability the second ball is red is R over R plus S. Now, we put in some work to get here, and we're tempted to say, oh, we're tired, we want to take a break, but we should always look back when you get an answer. Does it illuminate the problem? Can I verify it by direct methods? Is it intuitive? Now, this expression R over R plus S looks familiar. Have I seen this before? Oh, yes, indeed, we have. It is exactly the probability of drawing a red ball on the first draw. So the chance of drawing a red ball on the first or the second draw is the same. Is this surprising? You should pause and think about this. Perhaps then you might conjecture the chance of drawing a red ball in the third trial is also the same. Try it. See if we can verify this. See if we can then come back and say, ah, I get it. This is why it should work. This is what I mean by an answer illuminating a problem, showing you unexpected crannies and nooks that you might not have anticipated at first blush when you first saw it. All right, let's move on. The question at hand is a conditional probability. What is the chance the first ball drawn is red, given that the second ball drawn is red? Well, let's write it down mathematically. From the point of view of a definition, we can write down the conditional probability as a ratio. But the whole point of the exercise is the object in the denominator can be expanded out using total probability. In other words, we have just used Bayes' rule. And now we've got a simple ratio of fractions, cancel out terms, and we've got again a simple expression, r plus a divided by r plus s plus a. Again, we should ask, does this say anything about the problem? And staring at this fraction, it becomes clear, as an easy exercise in clearing denominators will show you, that our answer is larger than the fraction r over r plus s, which is exactly the probability of drawing a red ball on the first draw. And so our expression tells us that the conditional probability of drawing a red ball on the first draw, given that a red ball was drawn on the second draw, is larger than the probability of drawing a red ball in the first case. I wonder if this is reasonable. Do you see any connections to anything that we've already seen? Somehow the conditional probability has increased. If on introspection you said, that looks a little bit like Laplace's law of succession. Repeated occurrences of something predispose an increased chance of something having happened. And now I understand the connection. I say, yes, of course. If you tell me that a red ball was drawn in the second draw, it is intuitive that there's a heightened chance of having a larger population of red balls after the first draw. Okay, so this is very intuitive. But of course, our actual expressions adds precision to these verbal bones. It adds flesh to this. It tells us precisely, quantifies exactly how much the odds have improved. Now let's move on to the original question we started with. And this, of course, is going to require a little more elaborate calculation. But now we've got the structure of the calculation under our belts. We understand exactly what's going on. So here's our new problem. Given that the second and third balls drawn are red, what is the chance that the first ball drawn is red? Okay, and again, you should keep the tree in front of you, because that is going to allow you to write down, just visually, the kinds of expressions you need. Let's first express the probability at hand mathematically. We are interested in the conditional probability of the event R1 given the joint occurrence of R2 and R3. The definition of conditional probability allows us to write it down as a ratio. And now we see that we're all primed for total probability and Bayes' rule. Now let's work through the steps. First, the numerator. What is the joint probability of drawing 3 red balls in a row? Immediately, the structure of the transitions suggests that we apply a chain rule. The probability of R3 given R1 and R2 times the probability of R2 given R1 times the probability of R1. Notice this decomposition is in the forward direction because that is what is known to me. That is what is given to us. And of course, once we have this, we just read things out from the edges of the tray and write down an expression. And now all that remains is to simplify it, pool terms, and you're done. What about the denominator for the conditional probability we started with? Well, things are set up for total probability. The natural partition is based upon what happened in the first step. Remember Lao Tzu and the Chinese proverb, a long journey starts with a single step. Well, what happened in the first step? You either had a red ball or a black ball. That naturally partitions the space, and so total probability allows us to write down the probability of interest that the second and third balls drawn are red in terms of what the first draw was. And now we simply read out the probabilities again. And there we go. Right. So we first start with a chain rule for each of the terms on the right, again by conditioning on what the first draw was. Now simply read out the various probabilities on the edges of your tree and write down what look like complicated fractions. But of course, now we can simplify this very, very quickly. Pool the denominator, collect terms in the numerator, cancel common terms in numerator and denominator, and ultimately obtain a fairly simple expression. We are now all equipped to go back to our starting question. The conditional probability the first ball drawn is red, given that the next two balls drawn are red, is now given by a ratio of fractions. Simply cancel terms, pool it, and obtain a very simple and elegant expression. There is divinity that shapes our ends when we get answers so beautiful, so simple, so elegant. The conditional probability of interest to us is r plus 2a divided by r plus s plus 2a. We should pause now and take a look at what we already know. We observe that this fraction is strictly larger than r plus a over r plus s plus a, which in turn is strictly larger than r over r plus s, and this is done by simply clearing the denominator and comparing terms. And so we've obtained, again, a reinforcement of this Laplacian idea. The conditional probability of a red ball in the first draw, given that the next two balls drawn are red, is larger than the conditional probability of a red ball, given that the next ball drawn is red, which is larger than the probability of drawing a red ball in the first case. The more red balls that are drawn later on gives you more and more reason to believe that you had a larger red population to start with. This was now the moral of the story. Of course, this example was rich, and you can see all kinds of connections to it as a first step in a very simple model of, for example, the spread of contagion. Our purposes here were to illustrate how, in an example of a fair amount of structure, with a fair amount of richness, there is ample scope for the application of total probability of additivity and reversing the direction of conditioning, Bayes' rule. Before we move on to conclude this lecture and this segment, we should pause and extract a little more information about the setting at large. Can we extend it profitably in other directions? Now, if you pause and think about the problem, A represents a number of variables. Ineluctably, A has to be some kind of positive integer, perhaps 1, 2, 3, 10, something like that. But if the student will go back and take a look at the analysis, she will find that nothing really precludes A being a negative number. So here is the question. What if the quantity A is a negative integer in Pólya's Earn scheme? Suppose for definiteness, A is minus 1. What is this equivalent to? Well, in the Earn scheme, this says that you start initially with R red balls and S black balls. You reach in, draw a ball, and look at it. Okay. The original model said, well, you put it back in and then put in A more balls of that color. But if A is minus 1, what you've effectively done is you've reduced the red population, if a red ball was drawn initially, by 1 unit. If a black ball was drawn initially, you've reduced the black population by 1 unit. In other words, this situation with A being minus 1 is equivalent to sampling without replacement. More generally, if A is a negative number, which is, let's say, the negative of the greatest common divisor between the integers R and S, then at each step you keep taking out A balls of a given color, and then sooner or later the urn will be empty. Okay. Now the student should go back and ask, are any of the calculations that we have done compromised? Do the calculations generally work? How far does the tree extend? Is it now an infinite tree or is it a finite tree? Do the conditional probability inequalities that we derived, do they still hold? What other application domains could this kind of extension fit into? Well, these are all profitable directions for inquiry, and I'll let you think about them.